Hi everybody, welcome to another video in Calculus 1, section 5.2, definite integrals. So what we did in the previous section is random sum. Now let's do that again. Let's evaluate and interpret the midpoint random sum for this. Notice that this is the random sum and never mention the area under the curve. Because this one there is a problem. The function y minus x squared is potentially being negative. So if we calculate the height of the function, evaluate at those points, the values of the function is negative. So the random sum will be negative. It is no longer the area under the curve. But we still can do the random sum, right? From 1 to 3, 4 equal space. So the width delta x b minus a over n from 1 to 3, meaning 3 minus 1 is the length, divided by 4 equal segment, that is 2 over 4, so 0.5. Right. Now, so we will have four equal segment from 1 to 3. So the increment is 0.5, so we have 1.5, 2, and 2.5. But this time, we use the midpoint to calculate the height or the values of the function. So the midpoint here, 1.25, 1.75, 2.25, 2.75. Right, so we use those points to find the values of the function, the height, the values of the function. So it's going to be the values of that times the width So this time we use the midpoint. Right, just like last time I will factor out delta x. So first I will enter the endpoints 1.25, comma 1.75, comma 2.25, 2.75, and store this into a list. And the function is 1 minus at least where. Of course, we can take off those values times. We can just take this. Take that times the width of 0.5 and then add all of them up. Here I will do the summation first. Second stat. Summation of that, and I factor out delta x just like the previous section, so I will times 0.5 and it will be negative 6.625. Right, so certainly the random sum works, but in this case it's no longer give the area under the curve. The width, we go to the next part of the section, net area and definite integral. Right, consider the region R bound by the graph from A to B. Some of it is above, some of it is below. The net area is the area part that lie above minus the area that is below. So we have net area. So the total area that are above and the area below. So the area always positive. The net area may not be negative. So distinguish between the area and the net area above minus the area below. And note that the area cannot be negative. The net area may be negative, depends on what we have here. In general, area cannot be negative, but the net area may be negative, depends on the problem. So the idea is we just can divide the interval into a bunch of sub-intervals. Pick any point in the middle to find the height, the area of one rectangle, add all of them up, give us the Riemann sum. So this is the general Riemann sum, is that the sample point can be any point in between. It doesn't have to be on the left, the right, or the middle. It could be anywhere in between the sub-interval. The reason for that is later on, we let the width of the rectangles goes to 0. In that case, whether the left point or the right point or the mid point, all of those are relatively, essentially the same point. If we take the interval getting closer and smaller, right? Now, if we just take any random point in the middle, then we would take delta x will be the maximum of all of those points. Now, after that, put everything together, we have the notation. If we take the maximum of the width goes to 0, so essentially the width of the rectangle gets smaller to 0, so that goes to 0. So essentially n will go to infinity. If the width getting smaller, the number of rectangles increase, so n will go to infinity. So essentially we do this, the sum of infinitely many rectangles. And to do that, the notation of this is the area from A to B of the function. I should not say the area, I should say the net area from A to B of the function dx. So we shorten the notation dx for delta x, the function of x bar sub k, which is x from A to B. So if we want to go from A to B, that will give us the limits for integral the function. And that in the next section we tie the indefinite integral we have in section 4.9 and the definite integral in this section. So the definite integral is the net area from between the limits of the function. Right? So it's no longer the area below the curve because the function could be negative. So we say the net area from A to B is given by that, and we call this as the definite integral from A to B. Right? So, theorem. If f is continuous on A to B on the bounded on A to B with finite number of discontinuity, then f is integrable on A and B. So here is some notation. This simple sign elongated s is called the integral sign because we talk about that in section 4.9. So this elongated s is the integral sign. Now we know why we use that notation, right? Because that relates to the sum. The sum is the sigma. Sigma is the Greek letter S. So we write the elongated S because it stands for the sum. Right? So that's why we use the notation. In the next section, we'll tie indefinite integral and the indefinite integral together into one theorem. Right. So the integral sign, which gives us the net area from A to B of the function times dx, and that equal to this. Right. So now let's see if we have that notation is the limit of Riemann sum for the function f from 1 to 3. So how do we express that into the definite integral? Well, simple enough, right? We know this one is an integral from 1 to 3. and this is the function. Delta x of k is dx. The function is 3x squared plus 2x plus 1. So we can translate between limit of a random sum to a definite integral with ease. Bottom line is, what does this calculate? It will calculate the net area, not area under the curve, the net area between the function and the x-axis. Depends if the function is positive or negative. Calculate the net area or the definite integral, not the total area. Right. Now let's look at some examples so we can have the idea of how this works. Use geometry to evaluate the following definite integral from 1 to 3 up to x plus 3. So to x plus 3, linear function, simple enough, right? F of x is 2x plus 3. When x equal to 1, x equal to 3. When x equal to 1, put 1 in here. That is 5. When x equal to 3, so we have that. When x equal to 1, the function is equal to 5. And when x equal to 3, it's going to equal to 9. So we have this function. And we will calculate the area, the net area between the function and the x-axis from 1 to 3, from 1 to 3. So we will have this area. Which is very easy to calculate. Just rectangles and triangle. If we split this in two, this area here, 2 by 5, so 2 times 10. 2 times 5 is 10. This area here is a triangle. 1/2 base of 2 times the height. The height is go from 5 to 9, therefore it is 4, right? From 5 to 9 is 4. So 2 and 2 cancel out. We have 4. So the net area between the function and the x-axis is 10 plus 4 is 14. So we say net area, which is the integral from 1 to 3 of the function. This case just rectangles and triangles, so it's easy to say it. It's going to be 14. So simple enough, right? Next, we have the function 2x minus 6. Or from 1 to 4. When x equal to 1 is negative 4, and when x equal to 4 is 2. From 1 it is negative 4, and 4 it is equal to 2. So this is the function, and we talk about the net area, which is the area between the function and the x-axis. This is not area in the curve, the net area. So that could be formed by from the function with the x-axis. So we're talking about these two areas. So this area Again, this is a triangle, 1/2 base times height, base of 2, the height is 4. Notice the area, this area is going to be positive. Area cannot be negative. The net area can be negative. Now we talk about this area, which is also 1/2 base of 1 times height is 2. 2 and 2 cancel is 1. Now next part, net area equal to the area that is above minus the area that is below. So the net area is -3. Therefore, the definite integral from 1 to 4 up to x minus 6 is equal to -3. Of course, if we use a calculator, in the next section we will learn more about that. So math, option number 9. We go from 1 to 4 up to x minus 6, variables x, and we have -3. So the net area is the area above minus the area below. That could be negative. That can be negative. Each individual area cannot be negative. So be mindful of either the area or the net area or the definite integral. Right. Now, let's look at this example. Use this graph and that to answer the question. What is the definite integral from a to b of f of x? So from a to b, the net area is what? 12, right? Area above is 12. So that's easy from a to b. Now from a to c, what is the net area? Above is 12, below is 10. So the area above minus the area below. And next, what is the net area from B to D? From B to D, the area above is 8 minus the area below is 10. Yeah, so the definite integral calculate the net area between the function and the x-axis from the boundary. Could be negative. But if I ask you what is the area from A to C, that will be different. If I ask for the total area, it's going to be different. So be mindful of the question. Right. Now we have some properties of definite integral. First of all, if we interchange the limit, if we interchange this limit, we will have to put the negative in front of it. Simply, if we take the width b minus a instead of a minus b, that will be different. That will be opposite, right? So that's why if we interchange the limit, that's going to be throw in the negative sign. If those limits are the same, if we have the same limit, then it's equal to 0. Right? So swapping the limits, we're going to have the negative of the definite integral. If the limits are the same, it is 0. Because if we talk about the net area from A to A, if this is a function from A to A, there's no width. If the width is equal to 0, the area equal to 0, right? Because if we go from A to A, the width is equal to 0. This next two properties are properties of integrals, or properties of summation. We can split, or we can take the constant outside. If it is a constant outside, it can be taken outside of it. So 3 and 4 is simple. Properties of summation. The last one say, if we go from A to B, we can go from A to C first, and then from C to B, which makes sense, right? So if we talk about the area from A to C, A to B, we can go from A to C first, and then we can go from C to B. In that case, the total area from A to B is equal to the sum of those two integrals, which makes perfect sense. And the theorem here says actually C doesn't have to be in between A or B. The point C might be outside, still works. Right, now let's utilize these properties and answer this question here. Now, if the integral from 0 to 5 of the function equal to 3 and 0 to 7 of the integral equal to -10, what is the sum, what is the integral, the definite integral from 0 to 7 of 3 times the function? First, we have the properties where we can take the constant on the outside, right? So we do that. And the integral of this is -10, so we just put -10. That gives us -30. Simple enough, right? Now, we get back to this, which is a little more complicated. What is the integral from 5 to 0 of 2 times f of x? Now, we don't have 5 to 0, we have 0 to 5. So if we want to, where we interchange this limit, we throw in an extra negative sign. And I forgot the 2, sorry. That 2 is a constant I will take outside. And finally, the integral given is 3 times -2 is -6. Simple enough, right? Now, how do we do this? We do not have the integral from 5 to 7. We only have the integral from 0 to 5 and 0 to 10. So how do we combine them? Well, they are the number 0, right? So why don't we put the 0 in between? So integral rather from 5 to 7, we can go from 5 to 0, and then from 0 to 7. So we split. I mean, it works for any numbers. That number may or may not be in between this number. It doesn't matter. As long as those are the same, this will be the same. So rather go from 5 to 7, right? Rather go directly from 5 to 7. We can go from 5 to 0, and then from 0 to 7. We still add, start from 5, go to 7. Alright, now what we do is we will interchange this limit and throw in the extra negative sign where we interchange the limit. And then from 0 to 7. Now we know everything. From 0 to 5 is 3 with an extra negative. From 0 to 7 is -10 combined, which gives us -13. Right? So if we have that, we just split the limits at the numbers that is convenient, that is given. So we choose 0 in this case. Finally, we can take out the constant 2. And we get rid of the negative if we interchange the limit. So the original is negative, and then we negate one more time, turn to positive if we interchange the limit, because the problem only gives the limit from 0 to 7, not from 7 to 0. So that's why we have to interchange the limit. Every time we interchange the limit, throw an extra negative, negative turns to positive. And that integral given is -10. Right. So 1, 2, 1, and 5. Those properties are the properties of the function with the same function but different limits. So 1 and 5 properties that have same function, different limits. Property 3 and 4, same limits, different function. So if it is the same limit, different function, we can just split them with no problem, because the limit are the same, different function, we can split. Because the limit are the same, we can split the function. Take the constant outside. Yeah. So we have different function here, but since the limit are the same, we can just do that. The function is 3. The integral from 0 to 4 of f of x is 3, and also from 0 to 4 for g of x is -2. So we have 9 plus 10 is 19. Right, so those are the properties of definite integral. If the limits are the same, we can split the limits or take the constant outside. If the function are the same, we can just split the limit. So same limits, split the integrand. Same function, we can split the limit. So notice the difference between those two properties. Right, all of those two have the same function but different limits. These have the same limit, different function. If we have the same limit, we can split the integrand. Right, that's what we have in this problem. Now we have one more properties that we will revisit in the next section. The function, the absolute value of f is integrable if this is the sum of the area. So what we have here, the net area is the area above, area above minus the area below. That is the net area. Whereas if we do the integral, that gives us the sum of the area, so the total area. If we use the absolute values, the total area is going to be the sum. So the difference between the net area, area above minus the area below, with the total area we just add all the area together. So this guaranteed to be positive, so the total area must be positive, because we add all the positive. Could be 0 if all of them are 0, but because all of them are positive here, it must be positive. The net area depends, it could be negative. Right, now we have some exercise here. Use geometry to evaluate the definite integral. By the way, like I said, in the next section we'll revisit this, but now just do more example. Use geometry to evaluate the definite integral from -1 to 3 of absolute value 2 minus absolute value of x. If we want to graph 2 minus absolute values is under math, go to second tab, that is absolute values of x. The graph is going to be upside down V. Zoom number 6. Upside down V. Let's zoom in. Right, so it is a V. Like that. This is usually absolute values is that. With the negative, it turns upside down and then plus 2 go 2 units up. So that's why it looks like that. Now in this case we want the definite integral, which is the net area. It's definite integral, same thing, from -1 to 3. Right, so just calculate the area of that. So I will split this into that rectangle, and then a triangle, and a triangle here. Right. First, this rectangle 2 by 1 is 2. That is above the x-axis. So if it's above the x-axis, it won't be positive. It's only go from -1, so we go from there, right? Go from that part on. This area is a triangle 1/2 base times height. The base is 2, the height is 1. So 2 and 2 cancel out. This is 1. And that area is above the x-axis. So we add to it the area above minus the area below. Next, we also have this area here. One-half base of 1 times the height is 1. So plus 1/2. And finally, subtract the area below. So this area is 1/2. Base times height is 1/2. So we subtract. We plus if the area is above, subtract if the area is below. Do all the math, and we have the net area equal to 3. 1/2 cancel 1/2. So the area above minus the area below, that gives us the definite integral or the net area. Of course, if we want to do using the calculator. Math number 9, going from -1 to 3 of 2 minus absolute values of x dx. It's 3, right? So definite integral is the net area between the function and the x-axis equal to the area above minus the area below. Next, find the definite integral if we are given this graph. So from pi over 2, we have r2, which is pi minus 1, and this is above. We add from pi to 3 pi, from pi to 2 pi, it's going to be pi plus 1, and that area is below the x-axis, so we have to subtract the area. If it is below, we have to subtract pi plus 1, which is this area here, and 2 pi minus 1, also below the x-axis, so subtract 2 pi minus 1. So we have pi minus 1 minus pi minus 1 minus 2 pi plus 1. So a pi cancel negative pi, a 1 cancel -1. We end up get the net area equal to -1 minus 2 pi. Let's see if this works. Keep the calculator in the radian mode, which is the case. Math number 9, go from pi over 2, go to pi, x sin x dx Here we have that number. Sorry. Go to 2x, right? I mean 2 pi. We have that number. And is that equal to minus 1, minus 2 pi? It is. So yeah, so that is correct. So for this section, we learned that definite integral could be negative. It is the net area between the function and the x-axis, which equal to the area above minus the area below. We don't do any math here other than using geometry to calculate the area. In the next section, we will tie all the theorems together. But that's it for this section. As always, thank you for watching. See you in another video in Calculus 1.